Alright, so I'm going to do a review of the recursive and explicit arithmetic and geometric formulas. This covers questions 8 through about 16 on the unit exam. And I'm going to go down to our learning target. So things that we should know by the end of this lesson. 1, we should be able to identify whether a sequence is arithmetic or geometric. 2, write a recursive formula using the correct formula for a given sequence. 3, write a sequence when given a recursive formula, so the opposite of 2. And then lastly, use the explicit formula for arithmetic and geometric sequences to find specific terms, whether that could be the 41st or the 67th term. All right, so let's start with part 1. Identify the type of sequence. So here what we are going to do is first understand what geometric and arithmetic sequences are. And even though the words may seem a little confusing, in an arithmetic sequence, you either add or subtract to get from one term to the next. For example, to go from the first term, which is A1, to the second term, A2, we are going to just add 3. Right, and then go from the A2 to the third term, A3, you add 3 again, and so forth, and so forth. So this would be called an arithmetic sequence. All right, and then geometric. If arithmetic is adding or subtracting, then for geometric, you're either multiplying or you're dividing. So we look at number 2, to go from 81 to 27, we're going to divide by 3. To go from 27 to 9, again, that pattern is divide by 3. You're repeatedly dividing by the same number, therefore, that is a geometric sequence. I'll leave numbers 3 and 4 for you to figure out, but using the examples from number 1 and 2, you can figure out whether it's arithmetic or geometric. And if you're not repeatedly adding or subtracting by the same number, and you're not repeatedly dividing or multiplying by the same number, then it will fall under that neither category. All right, part 2, recursive formula. The 2 things you're going to need to know for recursive formula is that it must include the first term given the sequence and the rule, or in other words, the expression that relates each term to the one before it. So it's how do I get from one term to the next? That's the expression. Expressions include numbers and operations. So take number 5, for example. Right, our first term, our A1. Remember that subscript does mean that it's the first term. A could be any of these values, but any of these values, is going to be the first term, or if there's a 2, then it represents the second term. So our first term, A1, is going to equal the first number in the sequence, which is just 10. And then the expression to continue, this sequence forever. That's where you see the dot, dot, dot. Means that it continues to repeat on and on and on, because we're constantly either adding by the same number or multiplying by the same number. We just need to figure out what our A1 plus 1 or AN plus 1 is. So this is N as a variable because it could represent any term number. The subscript does represent any term number, and plus 1 to the subscript number represents the next term. So AN plus 1 just simply is an expression to represent next term. So our AN plus 1, our next term is going to equal, or the formula to find our next term, our expression to find the next term, is whatever number term that we are referring to, whether it be A1 or it could even be A3, to get to the next term, right, what are we doing there? And number 5, you can see to go from the first term to the second, we're adding 5 to it. To go from 10 to 15 is plus 5. To go from 15 to 20 is plus 5. To go from 20 to 25 is plus 5. So our expression is adding 5 to that. So again, an plus 1, that's the subscript for the term number, represents the next term is going to be equal to whatever term that we're mentioning. You're going to add 5 to it. And again, n stays as a variable because I can use this formula, this recursive formula, to represent how to go from any of these terms to the next, right? To go from the fourth term, A4, to the fifth, I would use the same formula. All right, and that's pretty much it for recursive formula, other than, if you're not adding, then you replace the plus 5 with whatever you're multiplying, dividing, or subtracting. So for example, in number 6, to go from 64 to 32, right? Again, our first term is 64 because we always need the first term. And now we need the rule or the expression to continue this pattern on forever. That would be our next term, an plus 1, is going to be equal to, scroll down just a little bit, right? Any term number we pick to go to the next term, we're going to need to divide by 2. Right? And as mentioned before in class, dividing by 2 is the same thing as multiplying by 1/2. So both of these formulas, or both of these, mean the same thing. You could go with the first one, dividing by 2, or the second one, multiplying by 1/2. Either of those will get you the same result. So, like section 1, I'll leave numbers 7 and 8 for you to practice with. For part 3, they give you the recursive formula, and now you have to fill in the sequence. So again, A1 represents the first term. So that's the first number that's going to go into each of these places. An plus 1 means to find the next term, we're going to take any term number. In this case, we only know the first term so far. So we'll plug in our A1 value, which is 5. Right, for A1, that term value, we'll just add 3 to it. And that'll give us our next term. And then to go from A2 to A3, our third term, again, add 5 to it again. So it's the same as if we plugged in the value for A2, instead of n, we put A2, which the value is 8, then that will be 8 plus 3, right? Which means our third term, A3, would end up being 11. And that's all there is to recursive formula. Now, the other things to notice for this is a plus 3. If you look at the next formula, again, you started with 2. We're going to constantly be multiplying 3 here. We're going to constantly be multiplying times 1/2. We're going to constantly subtract 5 to go from one term to the next. All right, finally, in part 4, using the explicit formula to find the nth term. Nth term just represents any number term you're looking for. Again, whether it could be the 11th, or if it's the 5th, or if it's the 67th term, whichever term you're looking for, there are 2 formulas that you can use to find those term numbers. That's the arithmetic explicit formula and the geometric explicit formula. So we know an represents any term that we're looking for. A1 is going to represent our first term. N, again, is that term number that we're looking for. D represents the difference, which is simply what are you adding or what are you subtracting to go from one term to the next. All right. Similar with the geometric. Again, to find any number term, we have our first term. We multiply it times r. R equals r ratio. And again, this is geometric, so that just equals, what are you multiplying or dividing to get from one term to the next. Once you understand that concept, then it's simple as plugging in about 3 numbers in order to find that explicit term and then solving it using the orders of operations. So let's start with number 13, the arithmetic formula. Here we see that A1 is 5 and our difference is 10. So we'll start with the number 5 and we'll constantly be adding 10 to go from the first term to the second, then the second term to the third, and the third term to the fourth. You just keep adding 10. Now you could do that till you get to the 11th, but when the numbers start to get really large, like 67th or the 90th term, then you want to have a formula to get there quicker. That's what the explicit formulas are for. So now we're going to look at the formula for the arithmetic explicit formula, and we're going to plug in these values. Again, whatever term we're looking for, the first term, and the difference. If it's geometric, then a ratio. It's 3 things that need to be plugged in. All right, so the number term we're looking for is 11. So instead of AN, we'll put A11 equals the first term value, which is 5, plus N. Again, N is the number that we're looking for. We're looking for the 11th term, so 11 minus 1, times D, our difference, which is 10. All right, we can use the order of operations. Parentheses are first, so 11 minus 1 gives me 10. So now I have 10 times 10 plus 5. Again, orders of operations. Whenever you have a number in parentheses next to a number outside, that means multiplication. We always multiply before we add. So we'll do 10 times 10 first, which is 100, and 5 plus that 100, meaning that our A11, our 11th term, will be equal to 105. And that's how you use the explicit formula for an arithmetic sequence. For a geometric sequence, it's pretty much the same, but instead of plugging in the difference, what are you adding or subtracting by, you'll be plugging in the ratio, which is what are you multiplying or dividing by. So again, to find the AN, any term that we're looking for, in this case the 5th term, so A5 is going to be equal to the first term. The first term in this one is 5, times the ratio, which our ratio here is 3. And then we have an exponent of n minus 1. Again, n is that term number that we're looking for. Right? Instead of the nth term, we're looking for the 5th term. So replace that n with 5 minus 1, which simply simplifies to 3 to the 4th power. Once you plug in your correct values, then again, solve it using the orders of operations, PEMDAS. Please excuse my dear Aunt Sally. We know that exponents, parentheses, come before exponent. So we solve within the parentheses first. We did that. 5 minus 1 is 4. Then 3 to the 4th power, we do exponent second. So remember that exponents are just simply repeated multiplication. All right, so 3 to the 4th power is 3 times 3 times 3 times 3. 3 times 3 is going to be 9. 3 times 3 is going to be 9. 9 times 9 is going to be